Good evening, all. Welcome to the live session for the course Matlab Programming for Numerical Computation. Let's wait for like few more minutes to see if there are more people to join the class, and then we'll start the session. So whoever is there in the session, please to stay. We'll start in like few minutes. Good evening. Let's begin the session. So, so as we used to do in every classes, first we'll be doing a quick recap of whatever was taught in this week. And you can ask me doubts if you have any, and then we'll be doing some problem solving. It will be similar to the ones that we'll be getting for our assignments. So it will help you solve your assignment problems also. So I hope my PPT, you can see the PPT. So let us begin. So here this time we'll be solving how to do numerical integration and numerical differentiation. So first let us look at differentiation. So the differentiation, this formula, like this formula, you would have seen it in mathematics. in your earlier classes also. That is, if you have to differentiate a function f dash of x, just give me a second, let me just annotate. So if we have to find the derivative of f dash of x, now we had a formula that f dash of x is equal to limit h tending to 0, f of x plus h minus f of x divided by h. That is, if you have a function like this, something like this, and this is your x-axis and this is your function value, f of x. So if I want to calculate the derivative of this point, what happens is, if it is x0, I take a small step size h. Okay, this step size is small h, and I get a x0 plus h point. So I have like x0 plus h and x0. So if I want to calculate the derivative at the point x0, that will become f of x0 plus h minus f of x0 divided by small letter h. And we let us assume that we are taking a very, very small value of h, then you can approximate this. So then this equal to, we can approximate. It becomes f of x plus h minus f of x divided by h, provided h is a very, very small value. Now, this is the same thing you get from the Taylor series expansion. For example, if you are approximating the value of x plus h, function value at x plus h, it is taken as f of x plus h time f dash of x plus h square plus f double dash of x, and so on the higher order terms you have. Okay, so on you have the higher order terms. Now let us assume that we are truncating it here. So this is, let us truncate it here. Then what happens is you have to divide the whole equation by h. When you divide the whole equation, so this was the order of this expression was in the order of h square. Just a second. Okay, this expression is in the order of h square. What we do is we'll bring this f of x to this side, and let us put an equal to symbol here. Okay, and you divide the whole thing divided by h. When you divide the whole thing divided by h, here you will have an h. This will be cut off, and this will become h. So this will become order of h now, because h square I divided by h, now it is order of h. So this is the expression that you get. So f dash of x is equal to f of x plus h minus f of x divided by h, plus there is an order of accuracy. Okay, this could be minus or plus, that doesn't matter, just that the order of accuracy is the order of h. This we have already seen what does this order of accuracy means. For example, if you are calculating, you have seen that there is something called as an error term, and then there is an h term. So means that order of accuracy means if I'm varying h by a factor of 10, my error also reduces by a factor of 10. Okay, if I'm reducing h by a factor of 10, my error also drops by a factor of 10. That's what is meant by order of accuracy. Any doubts in this slide so far? If not, let us move on. So next we have the derivative formulas. So these are the forward difference formula which you have already seen. That is f dash of x is equal to f of x plus h minus f of x divided by h plus, or then the order of accuracy is h. Now the other formula what we have is the backward difference. So instead of taking a forward step of x plus h, what we do is we take a backward step of f of x minus h. So here the formula you have to make sure, here you have to make sure the order is right. First you take f of x. Uh, just a second. Yeah. First you take f of x, then minus f of x minus h divided by h, and this also has having an order of accuracy of h. So the forward difference and the backward difference, I hope it is pretty clear. And one more example I'll say is that if you have a function, for example, it is starting from here. Okay, it is starting from x is equal to 0. You have a function like this, some function like this f of x. Where do you apply forward difference? So if you're taking the starting point doesn't have a back point. Okay, it doesn't have a previous point. So here you have to take forward difference. If you need to find the derivative of the starting point, you'll have to take the forward difference, because forward, when you move forward, you'll have a point. Now coming to the last point here. Now coming to the last point here, what happens is, when you move forward, there is no function value. So at this point, you'll have to take a backward difference. Okay. So there is a backward difference and forward difference. That this is where we apply. No, it's not neat. Let's do one thing. I'll do it once again. So if we have a curve like this, at the starting, you will have to take a forward difference, and at the end, for example, the function goes like this and the function ends here. Okay, imagine that. Now at this point, if you need to calculate the derivative, you will take a backward difference. And in between, you can take either a forward, backward, or central difference. Now let's look at the central differencing formula. In central differencing formula, what we do is if you need to calculate the derivative at a point of x, you take a forward step, you take a backward step, and you subtract this two. And now what will be the step size difference? So what happened is here you have h, okay, you have moved forward by a step size h, you have moved backward by a step size h. Now the total step size is what? H plus h, you have a step size of 2h between the x plus h and x minus h. So that's what you get here. You have a step size difference of 2h. And here the most important part is it is having an higher order of accuracy. That is order of accuracy is 2. That is, if I'm reducing h by a factor of 10, my error reduces by a factor of 100. So this is what is meant by order of accuracy. So what happens is for the same point, if you're calculating derivative using forward difference, central difference, and backward difference, this one will give you lowest error. Okay, this is the most accurate. Central differencing formula is the most accurate one. Any doubts? If not, let us move forward. Now, so as we discussed, the order of accuracy of forward difference formula is this one. Backward difference formula is h square. And sorry, central difference formula is x square and backward difference formula is h. Now we will have to understand the trade-off between the truncation and round of errors. So before that, let me just show you some Matlab problems. Just give me a second. I hope you can see Matlab. So let's see first an example. So the question is to find the derivative of tan inverse of x. Okay, so that is a question that we have here right now. So the question is find the derivative of tan inverse of x. So just a second. So question is find the derivative of tan inverse of x. Now, actual tan inverse of x, what is the true value? If we have taken, if you look at the trigonometric formulas, the actual derivative of tan inverse of x is 1 divided by 1 plus x square. So we need to find the derivative of tan inverse of x at the point x is equal to 1. Okay, so that is the thing that we have. Right now, I'm giving that variable x is equal to 1. I'm calling that point as a equal to 1. So my true value will be 1 divided by 1 plus a square. Now next is I have to take a small step size of h. So initially I'm taking a very, very small step size of 1 divided by, 1 e raised to minus 4. Now let us apply the forward difference formula. So in the forward difference formula, what happens is you have to calculate. So in tan inverse, in Matlab, it is written as A tan. Okay. A tan is equivalent to tan inverse of x. In Matlab, this is the command that you take. So in tan inverse, what happens? You take a step size in front, that is a plus h you take, and then you take tan a, okay, at the same single point and divided by h. Now we also calculate the error in the forward differencing. That is absolute error difference between the true value, that is this value, and the value that you got from the forward differencing. That is the error. And you print the error. This display command, I'm sure that you already know, that is disp. You have to divide that into num into str, error forward. Now going forward, we'll look at the central differencing. For that, you have to move a step forward, move a step backward, divided by 2h. And when you find the error, you can find the difference between the true value and the central differencing, and you just print it down here. And for the backward differencing, what you do? You have to take the point A minus H, you calculate the error and you print it down. So let's see how the error is. So let me run this code. Now we will see that the true value, that is tan inverse of x, the derivative is 1 divided by 1 plus x square. When x is equal to 1, the true value is 0.5. And let me just calculate, let me just write the FW D BK BKD, and the other one was CTR. Yeah. So here it might not be very clear because everything looks like 0.500, 0.500. Let me just look if we can see the decimal points here. Okay, it's because 000 and the error happens in the very last decimal places. But you can see that the error that you get with forward difference is order of e raised to minus 0.5, and the error that you get with central differencing is actually lesser than that. That is e raised to minus 10. And the error that you get with backward differences again is the order of e raised to minus 0.5. So this is what I meant. For the same point, if you are applying central difference formula, you will be getting the more accurate results. Okay. I hope this is clear. Now moving on to another example. Just a second. Okay. Now let us see what will happen if you are varying the step size h. So the earlier the step size that I was using was e raised to minus 0.4. What we'll do is we'll vary the step sizes and we'll see how the reaction is changing, how the error is changing. So again, a is equal to 1. True value is equal to 1 divided by 1 plus a square. And now instead of taking a single value of h, I am taking a vector of h. So that will be, I'll just print that vector value of h here. That'll be 0.1, 0.01, 0.001, and so on. Okay, so this will be the different values of h that I'm taking. Now what I do is I have to calculate the forward difference. So in the forward difference, you have to say that a tan, so I'll just run this code here. Okay, a is there. Let me just clear once. Running this section here, you will be getting a value to be 1 and you have h as a vector. Now what you have to do is you have to calculate a tan a plus s. When you do a tan a plus s, okay, a tan a plus s, this is what you get. Since h is a vector, a plus h is also a vector. Okay, here h is a vector. So h is a vector. So a plus h is also a vector. And when you take tan a plus h, that also becomes a vector. So what happens is I'll just print this here. And you will be getting, this is tan of a plus h when h is equal to 0.1. This is when h is equal to 0.01 and so on. You'll be getting the tan inverse. But a tan is a scalar value. See, a tan h is a scalar value. So now vector minus a scalar, you can do it. That is feasible. But we can't divide the vector by a single value. Okay, vectors cannot be divided like this. Only scalars can be divided. So what do? Is we do a dot operator, a dot division here because h is also a vector here. So what happens is now the forward difference, the derivatives look like this. Let me just run this section. Okay, you will be getting these many values corresponding to each of the h values. And the error also you will be getting as a vector. See, this is each value will be subtracted with the true value, and that is the absolute difference that you get. Now, the error that you get will be a scalar. Sorry, will be a vector, not a single value. See, the error that you get with forward differencing is of this order. So now you can see earlier it was 0.02. Again, it was changed when I decreased h by a factor of 10, my error also decreased by a factor of 10. So you can see that here. I decreased h by a factor of 10, error also decreased by a factor of 10. Again, I'm decreasing h by a factor of 10. Again, it decreased. One more zero got added. So on. So now let me just run this code and show you what's the difference. The same thing I'll do it for central differencing, just that the formula has to be different for central differencing. I do a dot division, then I calculate the error values and I print it down. Backward differencing also I do it. Now, if you want to find the order of accuracy, what do? You have to plot the log-log plot, what we used to do in our previous sessions. So log-log plot, you have to write first H error forward, which is a blue line, then H error center, which is a red line, and H error backward, which is a magenta line. Now, let me run the whole code. Okay. This is the plot that we get. And if you look at the value, you can see when I decreased H by a factor of 10, both my forward differencing. So when I decreased H by a factor of 10, both my forward differencing and my backward differencing also decreased by a factor of 10. But here, if you see, here it was 10 raised to, so that is 8.3 into 10 raised to minus 3. And this is 8.3 into 10 raised to minus 6. And this is 8.3. So this is what, not 3, it is 4, right? Yeah, it is 4. And this becomes 8.3 into 10 raised to minus 8. So by decreasing h by a factor of 10, I decreased. Okay, just a second. So in the central differencing, what happened when I decreased h by a factor of 10, my error decreased by a factor of 100. H I decreased by 100, 10, and my error decreased by 100. Okay, that is what is meant by order of h square. Is this clear? Can you see that? And that is exactly what you see in the plot also. If you calculate the order of accuracy, that is, let us calculate the slope for once. So, do I already have it? Yeah. So that will be uh, slope 1 is equal to log, okay. Is my bracketing correct? I think. You can directly calculate the slope. Yeah, I'll be getting almost equal to 1. Okay, it will be like 0.99, which is equal to 1. Now, if you're calculating for CTR, okay, that is error CTR. We'll be getting 1.99, which is close to 2. Okay, that's the slope that we get. Is this clear? This is the formulas, and that is the slope of the line here. You can calculate the slope of the line here, and you'll see that both the lines are overlapping here. Both the pink and the blue lines are overlapping here. That is the forward and backward difference. And the higher slope is for the central differencing. Is this clear?
Now, one small doubt.
Yeah, sure.
Instead of the element-wise division, can we use a for loop, no? For loop
Uh,
there? Because
for
element-wise we are doing that.
Yeah, you can use for loop also. What you can do is in every loop you can take a particular a plus h, and you can divide that. Yeah, for loop can be done also. So for
Oh,
example, it will be like for loop is equal to, you have to root over like 1 to the length of h or something. Okay, so that you reach till the last edge, and in the for loop you can calculate tan sorry, a tan a plus, and h is a vector, right? So in h you can take if I is equal to, okay, hi, and then you can take a tan a something, and then you can divide it by h. So now h is a single value. Hi you have to take. Now it will be a single value.
Okay.
Yeah. So now I have like, so the same thing, now we had varied h from -1 to -5, 10 raised to -1 to 10 raised to -5. Now what if I'm using a further lower value of h? So that is what I've said here. So -1, instead of till -5, I'm going till -10. That is even lower value of h. What will happen? Let's run and see. Just a second. So this is the plot that I get. Okay. In the earlier plot, we only got this slope. We only got this slope. Now you have like a point here. Why is that so? That is because even if you keep decreasing the value of h like extremely small also, there is no guarantee that you will be getting the most perfect answer. Because as we said, discussed in the first lectures and all, there is something called as roundup errors and truncation error due to the machine precision. That is MATLAB has a capacity. So beyond that, you will not get a lesser error than this. So that is what happens when you keep decreasing h, your h value keep decreasing and you'll be getting the lowest error for a particular value of h. After that, what happens is your error value keeps increasing. Okay, and this is because it is kind of competing with your machine precision. Okay, so there is like no guarantee that the smallest, if you use the least value of h, you'll be getting the right answer. Always try to use an optimum value of h. Now moving forward, just give me a second. So this is for a different example. That is, you have a question that the function is 2 minus x plus ln x. So in this case also, we need to find the derivatives. So what do? We need to find the derivatives in the sense. Oh, sorry, this is the higher order, right? I haven't covered that in the slides. Just a second. So differentiation of single variable, that is second derivative. So far we discussed first derivative. For calculating first derivative, we have three formulas: forward difference formula, backward difference formula, and central differencing formula. Now let us talk about the second derivative. In the second derivative, we usually have the central differencing formula that is like this. If we have to calculate the second derivative of point xi, you have to take f of xi minus 2 times, f of xi plus 1 minus 2 times xi and plus 2 times xi minus 1. This is nothing but x plus h, x and x minus h. Okay, that's what it means. And divided by h square. And this method also has an order of accuracy of h square. So now let us try to find the second derivative of this, first derivative and second derivative of this question. This is the first derivative. You can calculate it manually. So this is a constant, so 0, then minus 1. And for log s, it is 1 by x. That is what you get here. Okay. Now if you again derivate, what will happen is this will become 0 and you will have minus 1 by x square. That is what you get here. Okay. So these are the true values. Now let us try to code that in MATLAB. So coding in MATLAB, what we do is this is the function. I need to calculate the function value when x is equal to 1. So a equal to 1, I am using a small step size of h is equal to 1 raised to minus 4. This is my true value for the first derivative, 1 divided by a minus 1. And this is my true value for the second derivative, that is minus 1 divided by a square. So now you calculate at a plus h, what is my value? Okay, this is my a plus h, what is the value? When x is equal to a, this is my value. When a minus h, this is the value that I have. Now using central differencing, this is for the first derivative, right? f1, that is at a plus h. So this is nothing but f of a plus h minus f of, sorry, a minus h divided by 2h. That is this function. And this is the central differencing formula for the second derivative. That is f of a plus h minus 2 times f of a plus f of a minus h divided by h square. That is this formula. Now what you do is You have to calculate the absolute errors between the first derivative true value and the what we got using the formula, and the second derivative true value and what we got using the formula. Now let's run this. Okay, this will be the error that you'll be getting. It is very, very small. And if you calculate what is the actual value, let me just calculate the actual value. That is, this is the first derivative value, and this is the second derivative value. Okay, if you want, you can confirm. Okay, when a is equal to 1, it will be 1 minus 1. It is approximately equal to 0. This value you can see it is very, very close to 0. Okay, it is e raised to minus 0.9. Next is minus 1 divided by 1 square. So this answer should be close to minus 1. That's what you get. Then second value is minus 1. Is this clear? Any doubts? If not, let's move forward. So now we have a physical example. This is R is given as a function of temperature. R is equal to Ke raised to minus E by RT, concentration raised to 1.25. And the value of K is given to you, value of E by R is given to you, and we have to find R dash, that is derivative of R at T is equal to 600 using central difference formula and C is equal to 1. So T value and C value is given to you. Now there is something called as optimum value of H, right? So this is a usual assumption that we take. That is machine precision raised to 1 by 3. And machine precision, you know how to calculate it. Just type EPS. That will be the machine precision. Go to Matlab. So let's type EPS. You'll get a value. And if you want to know what this EPS signifies, okay. EPS is a spacing of the floating points. That is a positive distance from the absolute value of x to the next larger value of magnitude floating point. So this is like the least count or something that you can see. For the you have a centimeter scale and everything, right? So just like that, this is the least count of the MATLAB calculations. So usually what you have to do is an optimum value of h is usually for forward differencing and backward differencing, it is ESP raised to 1 by 2. So that is approximately 10 raised to minus 8 for forward differencing and backward differencing. This you have to take h to be equal to e raised to minus, 10 raised to minus 8. And for central differencing, you have to take an approximate value of 10 raised to minus 6. Okay. So here what we have said is, here they have said that you need to calculate the derivative of this. T value is given to you, C value is given to you. Now let's calculate. Other constants are also given. K value is given, E by R is given. Now let's calculate. So this is the function that we have. R is equal to K plus E by RT, K plus E raised to E by RT, C raised to 1.25. And this is the actual derivative with respect to T. Okay, understand that this is with respect to T. C is considered as a constant. So this is the actual derivative. K is given, E by R is given, C is given, T is given to you. Now differentiation, this is the actual value. Okay, now the true value is, okay, true value, if you see, this formula can be simplified. Okay. So what happens is when it is divided, when it is a derivative of t, see this part remains constant. And exponential means this part, e by rt term comes to forward. And since it's 1 by t, derivative of 1 by t is, so the derivative minus 1 by t is 1 by t square. So basically you'll be getting this expression multiplied by e by r t square. Is this clear? Okay, this will be the true derivative. Now what we do is I am taking different values of h. I am taking like e raised to minus 3, e raised to minus 3, e raised to minus 4 till e raised to minus 7. And in the question they have said that take it as a multiple of T, the temperature. So that is we have taken H is equal to like this. And now we calculate the forward value of the function. This is the backward value of the function. And when you divide that, divided by 2s, this is the central differential formula for the first derivative. Now let's calculate the difference between the true value and the num value. Let's see. Just a second. So this is how we will be getting the error. So let me just open ERR. Let me just clear it first. Okay, this is the error that you get. Okay, so you can see initially the error was decreasing from 0.8, the minus 0.8 to minus 10 to minus 12. Again, it became minus 12 and then it increased to minus 10. So the least error you got it here. That is when at the third index. What is the third index H value? Let us look at that. When H value was 0.06. That is when you got the optimum error. This was the least error point. When H was equal to when H was equal to 0.006. Okay. Is that clear? Any doubts? If not, let us move forward. So far we were discussing about the single a derivative when we have only one variable that is changing. Okay. Now we'll talk about partial derivative. Partial derivative means there could be like multiple variables, and all of them are changing. It's not like any one of its constant. For example, in this equation we had like k was there. There are different variables. K was there, t was there, e by r was there, c was there. And but here it is only a function of t. K is a constant, E is a constant, C is a constant. T is the only variable here. But in this case, for example, f of x is equal to sine of x1 multiplied by exponential of minus x2. Here we are telling that both x1 and x2 are the variables. So we'll be group it together like a column vector. Here x1 is a variable, x2 is a variable. So now we will have two derivatives. That will be derivative with respect to x1 and derivative with respect to x2. Derivative with respect to x1, what will be? We'll be considering this part to be a constant. So exponential of minus x2 remains a constant. Derivative of sine x is cos x. So it becomes cos x1 e raised to minus x2. Now when you're derivating the same expression with respect to x2, what will happen? This part remains constant. And exponential of minus x2 is what? Exponential of minus x2 multiplied by minus 1. That minus 1 comes here. So these are the two partial derivatives. I'm sure that you know how to do this. Like we have done it in our earlier classes also. But in case you have any doubt, please do unmute yourself and ask. I hope this partial derivative is clear. So let's move on to the coding part. Okay, before that, we have one more thing. What if you have like multiple functions? Here, there was only a single function. When you have multiple functions, then the derivative is not a. So here, what happens is you have this function as a column vector. You have this as a column vector. Just a second. So you have this as a column vector, and this also can be arranged as a column vector. So in this column vector, what will happen is you will have dou of x1 divided by dou of x by dou of x1, dou of x by dou of x2. This will be a column vector. But what if you have like multiple functions? That is this case. When you have multiple functions, it will be a Jacobian. We have discussed Jacobian in the last lecture, but I'll explain once again. If you have multiple functions and multiple variables, so the function values are f1, f2, x2, and the variables are x1, x2, x3, and so on, then this is called as a Jacobian matrix. What will happen is, this is for the function f1 and the column. So this is for f1. So just a second. So this is for the function f1, the each row. This is f1. This is for f2. So on it will go. And this is for the last function fm. And each row will be for x1, x2, so on till xn. Okay, so this is dou f by dou x1, this is dou f1 by dou x2, and so on dou f1 by dou xn. So that's how you create the Jacobian matrix. You have to arrange each and every term like a matrix format, and this is the standard format. Each row corresponds to a function, and each column corresponds to a particular variable. Now we get the Jacobian matrix. Okay. Moving forward, the question is the same example that you saw, that is R is equal to K exponential minus E by RT, C raised to minus 1.25. Here we are saying that both temperature and concentration is a variable. So now you have two derivatives, that is dou R by dou T and dou R by dou C. How do you calculate? What you have to do is when you're calculating using, we can use the same differencing formulas, but just that you need to give the variables properly. So for example, imagine I need to calculate when temperature is equal to A1 and when concentration is equal to A2. Okay, this is the point that I need to calculate. What I know, so this one I'll put it in a column vector, A1 and A2. I'll put it in a column vector. Now what I do is, my function value, the function value I can calculate at A1, A2, but I need to calculate the forward and the backward value, right, for calculating using central differencing. So when I am calculating dou R by dou T, what I do is the forward differencing I only take at the temperature place. That is, I will only update this one. I will only update this one. So what I'll have is, I'll have A1 plus H, A2 remains as such, and I'll have A1 minus H and A2 remains as such. Okay. And let this matrix, I calculate what is the function value. I'll calculate what the function value here. I'll calculate the function value here. Subtract and divided by 2h. I'll be getting the derivative dou R by dou T. Dou R by dou T. Also remember that I can take separate values of h. This can be h value for, I can take different step sizes for both variables. So let me take h1 to be the step size with respect to temperature. Now what happens for dou R by dou C? This is the reference point, right? We'll only change this A2. So this becomes function value at A1, A2 plus H minus function value at A1, A2 minus H. And let the H be a different parameter, H2, divided by 2H2. This becomes by dou R by dou C. Do you have any doubts here? This formulas? So now, before going to the next topic, I'll just show the coding part of this. So this is the example, ke raised to minus e by rt. I'm taking c is equal to 1 and t equal to 600. This is my reference point. My partial derivative for the first temperature, I'm taking this as a step size, 1e raised to minus 6 multiplied by t. And for the concentration, I'm taking this as a step size, 1e raised to minus 6. And this is with respect to temperature. What happens? I only update the temperature value. T plus h1, that is this step size, comma c, and t minus h1, comma c. These are the two the column vectors that I had. Now what I do is I have a function here, my rate. This calculates a function value. That is my rate. It takes in a vector x. X will have two things. This x will have temperature and sorry. This x will have a column. X will be a column vector with temperature and concentration. Okay, that is why I take the first value of x1 is temperature, second value of x is concentration. K is a constant, e by r is a constant, and this is a function value. K exponential e by rt, c raised to 1.25. And that will be the output here. That will be the output here. Okay. Now I go back. So I calculate the function at x1 divided by the minus the calculation of x2 divided by 2h1. I get the derivative here. Now for the next point, I only update the C variable, C plus H2, C minus H2, and I subtract the values divided by 2H2. That is what is corresponding to the concentration. Now, if I print it, I'll get this partial derivative. This is dou R by dou T, and this is partial derivative dou R by dou C. So there is a mistake in the recording lectures. If you had seen it carefully, the recordings, this 2 is missing. Okay, it is only given 2H2. So when you do that, you will be getting an answer like this, 38.7596. But that is like a mistake. So just multiply 2 here. This is the actual formula. And so the actual answer is R is equal to dou R by dou T is, so this is dou R by dou R by dou T, and this is dou R by dou C. Okay, is this clear? Okay, now let's move on to the next session. That is numerical integration. So integration is actually, the meaning is to find the area under a curve. That is, if you're telling that let me integrate the function f of x, integration limit is a to b, I say that if my function value f of x is something like this, I find what is the area under this when the limit is a to b. So this area is called as the integration part, the area under the curve where the limit is from a to b. So there are several numerical ways you can find these derivatives. One of the method is called as a trapezoidal rule. So this is the trapezoidal rule. So that is when you have a curve like this, you draw a trapezoid. Trapezoid means you have like two parallel lines and these are unparalleled, not parallel. And what is the step size that you take? The step size. You have point A and point B. So the whole step size is nothing but B minus A. And here you can see that the actual area is this much. Actual area is this much, but in the trapezoidal rule, you're only getting this area. So this area is not calculated. So that is why trapezoidal rule is not a very accurate formula, but it's like a simple formula for calculating the area. This area is not counted. Okay. So trapezoidal rule doesn't work well when you have like a very, very curvy function. Okay. If the function is like almost like a straight line, then it can work. Okay. So this is the trapezoidal rule. Now let us go to the formulas that are more efficient than this trapezoidal. That is called as a Simpson's one-third rule. Simpson's one-third rule, what happens is if you've gotten an area, you divide the area into two parts. That is my derivative, my integration limit is from A to B. What I do is from this AB interval, I divide it into two. One interval, second interval. So now what is my step size? My step size is a plus a b minus a, and that is divided into 2. So I take the function value here, I take the function value here, I take the function value here. Okay, then I use the, so if you see the Simpsons 3 by 3 1 by 3 rule, it uses a plus h, a plus 2h. And what is h? H is nothing but b minus a divided by 2. Okay, so now you can see the area that has gone not calculated is very less compared to the trapezoidal rule. This is a small area, right? Only a small area is being avoided. Okay, this is more accurate than the trapezoidal rule. Now you have a function which is called as the Simpson's 3 by 8 rule. That earlier was Simpson's 1 by third. Now this is Simpson's 3 by 8. Here what happens is you divide the whole b to a into three intervals. So now what will be the function value you take? You take a plus h, a plus 2h, and this is a plus 3h. And a plus 3h is equal to, 3h is equal to b. So what is h? H is nothing but b minus a divided by 3. That is what you get. Okay, so this is the Simpson 3 by 8 rule. Here also you can see the lesser area is only avoided. Now this is the formula that we have for trapezoidal rule from limit a to b. Okay, you take h to be equal to b minus a, and this is a formula. F of a is used, f of a plus h is used, h by 2 is the factor that you multiply. And for the Simpson 1 by 3 rule, you have f of a plus h, f of a plus 2h, and h value is b minus a divided by 2, and the multiplying factor is h by 3. For Simpson's 3 by 8 rule, you have f of a plus h, f of a plus h, f of a plus 2h, f of a plus 3h. H value is b minus a divided by 3. And the multiplying factor is 3h by 8. Here, one thing you can notice, the order of accuracy for this method is h cube. This is h raised to 5. This is h raised to 5. So usually people prefer this method because it has a simpler formula compared to this. Compared to Simpson's 3 by 8 rule, this one has a simpler formula and you get the same accuracy. So usually people prefer this Simpson's 1 by 3 rule, okay, over than the Simpson's 3 by 8 because using a simpler formula, if you're getting the same accuracy, why do we do more calculations? Okay, is this clear? I hope it is clear. Now let us find this. Let us try to solve this question. The same function that we find the derivative for, that is 2 minus x plus ln x, we have to find the integral of this function using trapezoidal rule and Simpson's one-third rule and compare the two values. Now let's calculate. Uh, am I audible? Just a second. Let me just clear. So this is the function f of x is equal to 2 minus ln x. And my limit I'm taking a to be 1 and b equal to 2. And this is a true integral. Okay. The true integral is you will have, you can integrate this equation and see, and you have to substitute b and minus a. This is how you do it in max, the usual formula. And now the trapezoidal rule, what I do, h is equal to b minus a. I have written a function like this to make my life easier. So what happens is if you give a function value x, it will calculate 2 minus x plus log x. And remember one more point, in Matlab, log means natural logarithm. If we need log to the base 10, then there is something called as log 10. Okay. So log means natural logarithm and log 10, there is a command. This is to the base 10. Okay. So don't get confused. So this is 2 minus x plus log x. You calculate at a, you calculate at b, or else you can always write here a plus h. Okay, it will be the same thing. If you write a plus h also, it's going to be the same thing. And then you divide by the trapezoidal f of a plus f of b divided by h by 2. You calculate the error between the true value and what you got using the trapezoidal rule. Now Simpson's one-third rule is your h value is b minus a divided by 2. And this is your formula h by 3. Function value at a, function value at a plus h multiplied by 4. Okay, remember the formula correctly. And function value at a plus 2h. And again, you calculate the difference between the true value and what you got using the formula. Now, when I run this, I get the area I calculate using trapezoidal rule is 0.8486, and this is the error with the true value, 0.0397. It is okay, but the error is like pretty high compared to the Simpson's rule. In Simpson's rule, the area that I get is 0.8858, and the error value is this much. Okay, 4.5976 e raised to minus 0.4. This is very, very close to 0. So this is what I said. Simpson's rule is like more accurate than the trapezoidal rule. You're getting much more lesser error. I hope this is clear. Any doubts? Okay. Now let us go to the next topic. Let me see what the next slide is. Now, next we have is called as a multi-step trapezoidal or Simpson's rule. So here what we did is we applied Simpson's rule only once. And for that, we know this is the accuracy. That only once means if we had an interval A to B, using trapezoidal rule, the whole interval was a single segment. Okay. So the whole, if you had, so earlier if you see, the whole segment was a single section, A to B. And in Simpson's 1 by 3rd rule, it will divide into two sections. And Simpson's 3 by 8, it will divide into three sections. Now, what if our A and B is like very far away? Then we use trapezoidal rule, you will be getting a very, very bad result. Then what we can use is we can use multi-step trapezoid. That is, A to B, what you do is you divide into small, small segments. Okay. And the step size of H. So what happens is step size is H. So you have A plus H here, A plus 2H here, A plus 3H, and here you have A plus 4H, and so on till B. So basically, if you're dividing into n intervals, okay, n intervals, and your B should be equal to A plus NH. Sorry, okay, n intervals and A plus NH, this is n, okay, is equal to B. Then what is H value? H value is B minus A divided by n. This should be the H value. This will be the H value. So that's a formula that you see here. H is equal to B minus A divided by n. Now what you do is you take the first segment and you calculate trapezoidal rule only for the segment. So that is f of A plus f of A plus h divided by h by 2. That is for this area. You compute it for this area. Now you take the next segment. Here it is A plus h and this is A plus 2h. So A plus h, A plus 2h divided by h by, multiplied by h by 2. You get this area. And then you take the next segment, and so on. So you get I1 one area, I2 one area, I3 one area till the last one. Then what you have to do? Basically, if you sum up this area, you'll be getting the total area, right? So you sum up the whole integration formula. So if you sum up all this equation, it will look like this. H by 2, area of the first interval will only come once. Sorry, F1, F1, FA will only come once. You can see FA plus H is there in this formula and then this formula. So it get added up. 2 times f of 2. F of 2 is basically f of A plus H. And A plus 2H also got repeated twice. So that again comes here. And so on, it will be added. And the last value will also be repeated once. So this is a total formula. Okay, this is the total formula of the multi-step trapezoidal rule. What happens is you have to divide the interval into n, you have to divide the segment into n intervals, and for each interval you have to apply separate trapezoidal rule and you have to add it. Either you can use a for loop and calculate this and finally add it, or else what you can do is you can directly apply this formula. Both are possible. And what is the h value that you take? It should be b minus a divided by a. Is this clear? So this is a multi-step trapezoidal rule. We'll come to the other multi-step Simpson's rule also later. Okay. Now what you have to understand is earlier, if you remember, we have seen this multi-step formulas before. So then there is something called as local truncation error and global truncation error. Local truncation error is when you use one formula once. If you're repeating that same formula multiple times, what happens is the error gets accumulated. Okay. So then you have something called the global truncation error. So this is the table showing you that for a trapezoidal rule, local truncation error is of the order of h cube, but the global truncation error is the order of h square. And the same, this is h raised to 5, this is h raised to 4, h raised to 5, h raised to 4. I hope this is clear what is global truncation error and local truncation error. When you repeat the formula multiple times, the error get accumulated because there has been error in your first place itself. And it gets added up and then you have a different order of accuracy than the local truncation error. So that is LTE and GTE. Any questions? So apart from using these formulas, there is a method that you can, apart from using the trapezoidal rule, this long formula, in MATLAB, there is a function which you can use directly, which is called as a traps, and you have to give the x and the fl. So what is this x and fl? So imagine that you have a data like this. Okay, you have a data like this. This let it be x1, this is x2, this is x3. So basically this point, okay? Now let me just, okay. This is x1, this is x2, this is x3, x4, and correspondingly you have f1, f2, f3, f4, and so on. Right now? Okay. So now what happens is you have a vector. You have a vector x of x1, x2, x3, and so on. And correspondingly, you have a function vector. That is f1, f2, and so on. So this is what is meant by the formula here. X means this vector, fval means this vector. So if you're giving this vector values, the function points and their function values to the traps function, it will calculate the area under the curve according to the trapezoidal rule automatically. If you don't give the x, only the function value, what happens is it will compute the approximate integral of y. Basically, here instead of fval, if you're giving y, via trapezoidal rule using unit spacing. This x will be of unit spacing. Otherwise, x will be of the desired spacing as whatever you decide to. So let's do one. So this you can see, it computes the integral of y with respect to x using the trapezoidal rule. X can be a scalar or a vector with the same length as the first singleton dimension of y. Okay. So let's see using the code how to work with it. So the same problem, f of x is equal to 2 minus ln x. We need to find the integral. A equal to 1, b equal to 2, those are the limits. This is the true integral. And now we are dividing n to be 10 intervals. Okay. We are doing in the multi-step in 10 intervals. What happens is, for the trapezoidal rule, x is equal to b minus a divided by n. We already saw it in the PPT. Now your x value will be a plus h, a plus 2h. Basically, you can do that with the coordinate operator. A to b with the step size of h. And your function value is, if you can give that to this function. It will take the x vector and it will give the corresponding function value. So this is also a vector. Now what happens is I can either go by a for loop. So in for loop, what I do is, first I declare all the area intervals. Okay, this function is for calculating area of each interval in a vector form. So I let me say that, okay, all interval area is equal to 0. Now I run a for loop. Then I calculate for the first interval, it will be h by 2, the first function value plus the next function value. Okay, I get the first interval's area. Then again, when the loop runs, I'll be getting the second interval's area. So I interval is also a vector. Now, how to get the total area? I have to calculate the sum of the I interval. Sum of all the entries of I interval will give me the total trapezoidal, total error, sorry, total area according to the trapezoidal rule. So then I calculate the error between the true value and the trapezoidal, multi-step trapezoidal. I display it. After multiple application, this is the value that I get and this is the error that I get. Okay. Now, the same thing can be done using a direct formula. What do you do? The first value is only repeated once. The second to the last value. Okay. That is like second to the last. Basically, let me just do one thing. I'll just show you something. Clear. PLC. See, your n interval is n is equal to 10. Okay. This is your h value. Okay. If you have to divide 1 to 2 into 10 intervals, your h value should be 0.1. Now your x is a vector 1, 1.1, 1.2 till 2. Now your function value is also a vector. For each value of x, you get a vector. Okay. Now when I run this, let's see what this I interval is. The I interval is for each interval, what is the area? I calculate the sum of this total. I get the I get the total area. Now, one thing you have to keep in mind is that here my interval number was 10, right? But my function value is 11. So that is if I take n intervals, I'll have n plus 1 function values. Okay, so that you need to keep mind. So if you want, I can just show that to you here. See, I have like n intervals here. So this is first point. So imagine that 1, 2, 3, 4, 5 intervals are here. How many functions value you have? 1, 2, 3, 4, 5, 6. I have 6 function values. So if I have n intervals, I have n plus 1 function values. Okay, you should keep that in mind because indexing is very important in Matlab. Let me just share. So that is why you get this formula here like this. First entry is 1. The last entry is n plus 1. So if there are 10 intervals, there are 11 entries. So n plus 1 will give you the 11th entry. And 2 times the sum of the middle entries. So that will be the single formula trapezoidal rule. You calculate the error, you print the value. Now this is using the traps function. You have the traps function here. You give the x vec and the corresponding y vec. It will automatically calculate the area for you. You calculate the difference and you print it. Okay, this quad I haven't discussed, so let me just comment it off right now. Okay, I'll run this. This is what you get. Using multi-step, this is the area that I get. For h is equal to 0.1, my error is 0.00416442. That is of the order of basically 4 into 10 raised to 4, right? If I'm not wrong. Yeah, that is the error that I'm getting. So I get the same answer using for loop and using the single formula, I get the same answer. Using the traps also, I get the same answer because traps use the trapezoidal rule only. So I get the same answer and the same error. What if I am increasing the n divided n to 100? What will happen? Let's see. Okay. What happened is n I decreased by a factor of 10. My error decreased by a factor of 2. Now what I'm getting is 4 point. Sorry, this has to be minus. Okay, 4 into 10 raised to minus 6. So h earlier was 0.1, now h is 0.01. So h decreased by a factor of 10, my error decreased by a factor of 100. This means my order of accuracy is h square, right? So let's see if that is aligning with what was given in the PPT. Yeah, the trapezoidal rule, if you are using multiple step trapezoidal rule, the order of accuracy is h square. Okay, so that is if I decrease h by a factor of 10, the error will decrease by a factor of 100. Is that clear? This we have already discussed. Now I have a example question, that is if I have a interval values x going from -4, -3, -2, -1 and so on, and I have the corresponding function values, I need to calculate the area. So let's try to do that. And this has to be calculated using the trapezoidal rule. Okay, that is multi-step trapezoidal rule. So this is a code. These are the x values and the corresponding function values. What I can do is I can create a x is equal to 1. The step size of x is 1. From the tables, you can see that. So there are n is equal to 6 intervals. What you can do is you can run a for loop for each interval, calculate for each interval the area, and then what you do, you sum it up. So So this is what you get. The total area is equal to 34. You also can do it and compare your answer. The total area that you get is equal to 34 using multi-step trapezoidal rule for the following example. So this is like multi-step Simpson's rule. This is not shared with you in the recording lectures. I'm just showing it to you so that you understand how to calculate this multi-step. So in multi-step Simpson's rule, what happens is if you're taking one particular interval, that interval is divided into three portions, right? So with that we have f of a plus h, and f of a plus 2h. That is divided into three portions. If you take a next interval, that is also divided into not two portions. Sorry, Simpson's one-third rule is two portions. Okay, sorry here. Simpson's one-third rule is two portions. So that is why our formula is f of a plus 4 times f of a plus h plus f of 2 plus h. And the multiplying factor is h by 3. The same thing happens here. H by 3, f of a, 4 times f of a plus h, f of 2 plus a plus 2h. Okay. Then what you do is you do it for the second interval. That is starting from a plus 2h to a plus 4h. It ended here. A plus 2h ended here. Okay. So you start from here again, f of a plus 2h to a plus 4h. Then you start from f of a plus 4h to f of a plus 6h. And so on, it will go on until it reaches the end. So now what happens is you can either calculate it using single intervals and you can sum it up just like you did for trapezoidal. Or else when you add this formula, this is the final formula that you get. H by 3, f of 1, that is the first value, plus 4 times the f of 2, f of 4, f of 6. And 2 times f of 3, f of 5, and then we'll have the last value. Okay, then you can see a pattern here. Okay, the first value will be only repeated once. Then you have the second value repeated 4 times, third value repeated twice, fourth value again repeated 4 times. So you can see how you have to keep in mind this indexing. Okay, and then you can code this easily. And again, h is equal to b minus a divided by n. Okay. Now we have a question here. Evaluate the integral of e raised to x from 0 to 1 using Simpson's one-third rule, and n should be equal to 6. Let's code this. So here n is equal to 6, a is equal to 0, b is equal to 1. Your x is nothing but b minus a divided by n. So your x vector, it goes from a to b with a step size of h, and this is your function value. Okay, so this is the formula directly, h by 3. F of 1 is only repeated once. 4 times second index, fourth index, sixth index. Basically, the even indexes we repeated 4 times. Odd indexes we only repeated once, plus the last index. Okay, when I run this, you'll be getting the answer. The area is 1.7183. Is this clear? Any doubts? If not, let us move on to the next session. That is, we have a Matlab command which is called as quad. Okay, that is also used for calculating the area. So in this, what you have to do is it is based on Simpson's rule. It is not based on trapezoidal rule. And here, it's much more easier. You have to just give the function. Basically, if you have a mathematical equation like find the integral a to b for the function f of x, this f of x has to be given here. You give the limit a comma b. And in this f of x, you have to specify what is the variable you are integrating. So if x is the variable, you say this is the, by at the rate x, you mean that here in this function, it might have different variables out of it. The integrating variable is x. Okay. And this is an iterative procedure that this will end Matlab will end this calculation when the error goes below 1 e raised to minus 6. You can play around with this. There is something called as options available in Matlab. So I'll come to that. Let me just show you the example. Okay, the same question that we did earlier, I had commented it off. Okay, so the function which I integrate was this. That is this function. Okay, what I do is quad. I say x is the function variable. I write the function name and I give the just a second. I made a mistake. I say x is the function variable and the integration limit is a to b. So when I run this, okay, I should have ran this completely. See, using trapezoidal rule, I got 0.8863. Using quad also, I'm getting 0.8863. But the error, if you see, trapezoidal rule error is e raised to minus 0.6. And quad, the error is much more smaller, e raised to minus 0.8. Why? Because Simpson's rule is more accurate than trapezoidal rule. So that is why you get a lower error value here in the quad function. Is that clear how to use quad function? Let's move to the slides. So this is like an example question. So after this, we have problems. So this is a function f by k dx divided by 1 minus x 1.25. And you have to integrate from 0 to 0.5. F is given a value 10, k is given a value 5. So this is a function 1 divided by 1 minus x raised to 2.5. So let's try to calculate this. Okay, this is the function that I have. It will take the value of x. It will calculate f and k is given as a constant. Okay, and 1 minus 1 divided by 1 minus x raised to 1.25. It is good that when you have like the division in your formula, you always do point-wise division, okay? Because if you give x as a vector, this will say that the syntax is not possible. So always give like point-wise divisions. That is point-wise division and point-wise exponential. Now, when you have the function, this is the syntax. You have to just give quad. You say that x is the variable that I'm looking for. Quad reactor, I give x. Lower limit is 0, upper limit is 0.5. I get the error to be 1.5137. Is this clear? Any doubts? Okay. If not, let us go to the problem solving. So I'll show you problems. What you have to do is I'll give you some time. Try to do it using Matlab, or even if you don't have access to Matlab, take a pen and paper and try to code the lines. Okay, that'll be really helpful for you to solve your assignments and also for your coming final exams. So in case you have any doubts, you can just ask to me, like unmute yourself and ask. And if you get the answer, please put that in the chat box. We'll discuss. Okay. So we have an equation here. We have to find the integral of this using Simpson's one-third rule. And your limit is 1 to 2. And this is the true value of the integral. Okay. You have to use Simpson's one-third rule, single application. You have to report the value. You have to report the error. Then what you do is when x is equal to 0.1, you use Simpson's integrator multiple times, and then you calculate the error value. Okay, I'll give you a few minutes and then we'll discuss the answer. We have got some answers. Should I give you more time for others to do it, or should I start discussing the answer right now? I'll give you 2 more minutes. Okay. Then we'll discuss the answer. I've got some answers, so let's discuss. So first is a simple application of Simpson's rule. This is a function that we have. So let's go to Matlab. So this is a function, and the true integral is this: from a equal to b, sorry, a to b, a equal to 1 and b equal to 2. This is a true integral. So what we do is we calculate the step size difference, that is b minus a divided by 2. So this was for Simpson's one-third rule. This was your h value. For a, you calculate the function. A plus h, you calculate the function, or a plus 2h, you can calculate the function. If you don't want to repeat this 3 times, what you can do is this function, you can write it as a function form like this and call. That also can be done. Okay. Then what I do, Simpson's one-third rule, h by 3, f of 1 plus 4 times f of 2 and f of 3. Okay. Now I calculate the error between the Simpson's one-third rule, single time use, and the true value, and I print. So after printing, let me just show the code. I'll be getting error is equal to 0.00344 and the actual integral value is 1.26, yeah, 264. Many of you got the right answer. Yeah. So the answer is right. The first integral value is this, and the error is 0.00344. Okay, just confirm if you have not made any mistake, or if I have made a mistake, Jude, let me know. Okay. This is the error value and this is the integral value that you get. Now multiple application. So a equal to 1 and b equal to 2. This is a true integral value, just like we did before. What happens is, if you have to put x is equal to 0.1, you have to create a vector of x values from 1 to 2, the step size of 0.1. Instead of writing a function value repeatedly, I've created a function here. Okay, I can always create a function. I have to put here anonymous function because I'm not writing as a separate Matlab function. Okay, I can write a function here. Then I give the x vector here. I get the function value also as vectors. Now, what is the formula for multiple times? I is equal to h by 3. First value only repeats once. The even values, that is index 2, 4, 6, 8 until 10 it is there. So if I see here, let me just run this part. So here when I run this, I see there are 11 function values are there. So my even indexes means first index only once, 2, 4, 6, 8 and 10th indexes repeats 4 times. Now odd indexes 3, 5, 7, 9 repeats 2 times and the last index, that is f of x. Okay. Then I calculate the error and I print the error. So let me do that also. Mm, was it not possible? Okay, let me just write this as a separate function to avoid confusion. I think this is correct. If I've made a mistake in the formula, please do let me know. Still have that error. Double is not possible. Let me just run this section. But argument is double. I'll see what this problem is. Input arguments of type double means. Okay, I haven't saved this. Okay, again running this section. Yeah, I think I don't know what the error was actually. There is some, yeah, the way I wrote this could be a problem. So I've written as a separate function here. Okay, it takes the x value and it prints a function value for me. So when I get this, so let me run the total. PLC. Okay. So if I'm running it using a single Simpson's rule, this is the function value, this is the error value. And multiple Simpson's rule, the error value is 5.38 e raised to minus 0.6 and the actual value is 1.2606. Okay, I hope you got it right. In case you find any discrepancies here in the code here, which I showed here compared to the code you wrote, please do let me know. Okay, if I have made a mistake, I'll correct it and then I'll upload it maybe somewhere so that you guys can see it. So now moving on to the next question. This is integration. You can use the a of x sin x, a raised to x sin x is a function. You can use the MATLAB function quad, where first one a equal to, first subpart the a is equal to 2, and so it will become 2x sin x dx, x going from 0 to 1. And the next function is 4 raised to x sin x, x going from 0 to 1. This is very simple. I'll give you 2, 3 minutes and then we'll discuss the answer. Any answers? I've got one answer. So I'll give you 2 more minutes. We'll get the second answer also, and then we'll discuss. Okay. I've got some answers. Now let's discuss. Okay. So let me just share MATLAB quickly. So first I'm writing a function. This is a function that I write because in quad you have to give a function as an input. So this function takes in two input, x and a. A is the a raised to x, that variable that you have in front, and sin x. X is the variable you have to integrate with respect to. So prop to x a, and you get the function value as the output. Now in the function, what I do is quad, I tell that the integrating variable is x, not a. Okay, there could be other variables also, but x. Now prop to x, a is equal to 2, 0 to 1. And the next integral is quad, x is my integrating variable, prop to fund x, a is equal to 4, and integrating limits are from 0 to 1. So now let me run this. I'm getting the first integral value to be 0.7335 and the second integral value to be 1.1966. Yeah, most of them have got it right. Yeah, very good. Vikas and Purushot, I think I'm pronouncing your name correct. Both of you have got it correct. Nice. Uh, yeah, I want everybody to do like this, okay? And let me know the answers. Even if it is wrong, it's fine, but it's very important that you attempt it. Now, moving on to the next question. So, this is you have a temperature varying with time, and you have the overall model equation that is dt by dt is equal to minus beta times t minus 4. So, now in the problem, it is you have to find the central using central difference formula. First, you have to find dt by dt at t equal to 1. So imagine that at this point, you have to find t equal to 1. At dt by dt, central differencing formula means you have to use this value and this value. Okay, I hope that is clear. You have to find value at here. So you have to use, if this is a value, this is a plus h value, and this is a minus h value, and this is the corresponding function values. So you find dt by dt accordingly. Compute value of beta. Beta is what? If you have got dt by dt and temp t is equal to 1 here, right? 1 minus 4, you have to find beta value. Beta is the only unknown. Now we have to repeat the same thing for t equal to 3 and t equal to 4. You have to first find dt by dt, then find beta. Okay, this is the question that you have. I'll give you a few minutes and then we'll discuss the answer. In case you have any doubts regarding the question, please unmute yourself and ask, or else you can put it in the chat box. As we are running out of time, I'll discuss the answer. So let me go to Matlab. So this is the time and the temperature values from the table. For, yeah, I've got one answer. Yeah, okay. Let's see. So first, let us find d by dt at t equal to 1. So for that, we have to take this value, that is t index is 3 minus t index 1 divided by 2. Why 2? Because here the step size, if you see, yeah, I've got an answer. Step size, if you see, the step size is 1, right? So once I run this section, I'll be getting at t equal to 1, my slope dt by dt is equal to minus 5. Yeah, somebody has given me the answer. Good. Now next is I have to find the beta value. What is the beta value? I have to take minus t rate divided by the difference has to come. So beta value has to be computed for t equal to 1. That is uh, capital T index will be 2 minus 4. Okay. So now running this section, I get beta value at t equal to 1 to be 0.25. Yeah, we have got it right because. Okay. Now let us repeat the same thing for t equal to 3. Again, for t equal to 3 means this is the index. So corresponding to t equal to 3, it will be 16, right? So this is t for t5 minus t3. Okay, that will be the index. T5 minus T3, again, h is equal to 2, and the calculated value will be, let's run the section. The dt by dt is minus 3.25. Okay, just confirm it. For t equal to 3 minutes, this is a fourth index, right? So fifth index minus the third index for central difference formula divided by 2, you'll be getting the value, and the beta value will be 0.27083. Yeah, you've got it almost right, 2708, because it's right. And next is for t equal to 4 also, you repeat same thing. So it will be t6 minus t4. And the beta value when you compute, it will be dt value is dt by dt is minus 2.5, and the beta value is 2.3684. Yeah, good. You've got all the answers right. So that's it with the solution. I can just show you the code once again. And we move on to the next question. Okay, so this is, you have a function UA t minus 4. UA value is 120, and you have to integrate. T is the integration variable. You have to integrate from 0 to 5. You use trapezoidal rule, the given data. So you can use, this question is an extension of the previous problem. So this is the data. Okay, for time, okay, you have T and dt value. For time T, this is your temperature. So now you have to integrate this. Okay, you can use trapezoidal rule to find the next net h value, that is integral of this. Either you can use the trapezoidal rule, the formula directly, or else you can use the inbuilt MATLAB function traps. Okay, so if I want, this is the, just take note of this formula once. And those who have done the previous equation would have seen this table. Okay, so this is a table value. If you have a phone, just take a photo of it. Okay. And this is the formula that you need to integrate for. Yeah, second part. Is this okay? I've shared the second part. I've got some answers. So let's discuss. So first, if you remember for the trapezoidal rule, you have to give the function values, right? So going back. So first you have the T and the corresponding temperature, UA. We are dividing into how many intervals? 1, 2, 3, 4, 5. 5 intervals are there, UA is there. Either you can use the trapezoidal rule, so this will be the formula. That is, first you have to calculate the function. Function is what? UA T minus 4. Okay, that is the function value. So UA T minus 4 and your H is nothing but B minus A divided by N. That is multiple times the trapezoidal rule. That will be the formula. And you calculate for each and every interval. This loop we have already seen. And then you sum the interval, you get the net value, or else you can directly use a traps value. You have the T and corresponding UA you have calculated here. UA T minus 4. All right. So UA T minus 4 you have already calculated here according to the formula. And let me just clear CLC. When I run the code, this will be the answer. Using trapezoidal rule multi-step, it is 8910. Yeah, and using traps also, you get the same answer, 8910. It's the same answer. Okay, you can do either way, whichever you remember, you can do that. Okay, so this is the answer. You have got it right. Yeah, very good. Yeah, both of you have got it right. Good. Now, moving on to the next question. This is the last problem of the day. So you have here VL is equal to L di by dt, where VL is called as a voltage drop and L is the inductance. Everything is in SI units. Don't worry about that. I is the current, T is the temperature. Determine the voltage drop as a function of time from the following value. So L value is equal to 4. Okay. At every point, what you have to do is you have to calculate VL. So at this point, you have to calculate VL. Basically, you have to calculate di by dt at this point, di by dt at this point, and so on. At every point, you have to calculate di by dt and multiply it with L. Only then you will be getting VL at every point. And one more tip I'll give you. You know that central differencing is having the maximum accuracy. Okay. So for this point, you can do central differencing because forward there is a data, backward there is a data. So for all this from 0.1 to 0.5, you can do central differencing. But for this first point, there is no backward, there is no data. So for here, do forward differencing. Here or do here you can't do forward differencing because there is no data here. So here you do backward differencing. Here forward difference from 0.1 to 0.5 central difference, and for 0.7 you do backward difference for calculating di by dt. And you multiply it with L, you will be getting the VL value at each of the point. Okay. And then try to do it and I'll discuss the answer in like 2-3 minutes. got some answer. Yeah, let's discuss this. So, so this is the t value, I value, and n is equal to 4. For the first point, I'm using forward differencing. So T2 minus T1, okay, that is my H value. And my I value is it equally spaced? No, it's not equally spaced. Okay, so the H value you have to be careful. This is not 0.1. Here there is a jump. Okay, that H value you have to be very careful. And then you find the H value here, the step size value. You differentiate using forward difference. I'll print it out here. The rest all the points you do central differencing. So for the T2, you do T3 minus T1. That will be the H value here. Should I do? Yeah. So basically, you could have done this directly here. T3 minus T1. Instead of doing 2H, you could have done it directly here. That is I3 minus I1 divided by T3 minus T1. That is also possible. Now, central differencing, central differencing. At the last point, you do backward differencing. T6 minus T5 is the H value. I6 minus I5 is the numerator, the function value here. So now when I run it, this is what I get. Using forward differencing, I get 6.4. Yeah, 6.399, good value. 6.4, 6.4, 8, 5.6, 7.2, and 23.2. I have one doubt. Why is the fourth value decreasing? Yeah, fourth value could be decreasing. So the thing is, you're calculating the slope, right? So, uh, just a second. So slope means if you're, see, if you have your values like this, if your function value goes like this, it means the slope is positive. This is called as a slope, the tangent. But what if your function is having a dip like this? Okay, here the tangent is negative. Okay, so the slope can be, anyways, the slope can be decreasing. So here, I don't think the slope is negative here. The slope is, okay, the slope went up to 8 and then it became 5. This means here you can see it is steeper. But once it reaches here, you can see it is more like a flat region than a steeper region. Okay, that is what is meant by why is the slope decreasing. Okay, did that clear your doubt? And there are some discrepancies in the value. Just check the code. If I am making a mistake, do let me know. Okay, so this is the function value. Please be careful of the h because h is it's not equally spaced in the question. Okay, I'll just show the code once again so that you can take a screenshot or something when you're watching the recording. Oh, one mistake is there at 0.3, I think. Yeah, for 0.3 also, I use the forward differencing. Okay, why? Because, so that point I missed. Because this is not equal intervals. Backward and forward, there is no equal interval. This difference is 0.1 and this difference is 0.2. So that is why for the point 0.3 also I did forward difference. You can do backward differencing also, that is also fine. I can't do central differencing because the interval is different on both sides. 0.3 I used forward difference, 0.5 central differencing, 0.7 backward differencing. Now the formula is, final answers are this. I hope it is clear. Any doubts? Okay, as we are running out of time, yeah, thank you. So as we are running out of time, that's the last question that we have. I'll be uploading the recorded lectures and the PPT soon. So in case you don't have any further questions, you can leave the session. I'll be ending the session now. Okay, thank you all. I'll be ending the session. Thank you so much.